All right, so it's time for some kinetics calculations regarding nuclear processes. Now, we're not going to work a bunch of these because we worked a bunch of kinetics problems before. These are all first order, so they should be pretty straightforward. You might have to go back and review that part of the book a little bit if you kind of have maybe pushed some of that kinetics data off to the side in your mind as you did some of the other things. But let's look at a problem where we're presented with a question like this. Living wood has an activity. So when they say activity, that is a measure of how fast the radioactive decay process is occurring. Has an activity of 15.2 disintegrations per second. So that means 15.82 steps or individual decay processes in every second. And somebody's got a Viking artifact. And it's found to have an activity of 13.1. disintegrations per second. Now, it's not uncommon for this whole thing, disintegrations per second, to be just listed as per second. Okay? So our job is to estimate the age. So we use our first order kinetics, which says that the natural log of n over n0 equals minus kt. So to solve this problem, we need to know what k is for, and I guess I didn't say it, this is for carbon dating. So we need k for carbon 14. Now the way that we're usually given this is that for carbon 14, the half-life is 5,715 years. Some textbook use 5730, 5740, just whatever number you're given, go with it. So we're given a half-life, but we need K. So remember that the half-life is equal to 0.693 over K. And so from that, we get K to be 1.21 times 10 to the minus fourth per year. 1.21 times 10 to the minus fourth per year is the rate constant for carbon 14 dating. So now out of our problem we have n and n0. We know what K is. We can calculate how old that material is, or how long has passed since n0 turned into now n. Okay, so ready to solve the problem. So we rearrange. We want t by itself. T equals, we got to divide both sides by minus k. So t equals minus the natural log of n over n0 over k. Pause there if you need to and see how that rearranged, but that's what we get. The time that goes by is minus the natural log of n over n0, all divided by k. Those three values we know, and we can plug them in. Minus the natural log of n. N is our current time, 13.1, divided by 15.2, all over k, which was 1.21 times 10 to the minus fourth per year. That's where we're going to get our time unit out of this. Okay? I'll pause there. Make sure you understand, go back and watch again if you need to, understand what got plugged in where. Okay? then it's time to do some calculating. And somewhere I have a calculator. There we go. So 13.1 divided by 15.2 equals natural log of that, and flip the sign. So far I got 1.49 times 10 to the minus first divided by 1.21 double E 4 minus. I get an age of 12,278.9 years. But remember what I said about carbon dating. Don't put too many sig figs on this number. Sorry, I said 12,000, 1,200, my bad. So the answer I get is 1228.79. The better thing to say is probably about 1,200 years old. You put too many decimal places in here, you're giving nature too much credit for not having changed little things over time. We don't know for absolute certain that the carbon-14 content in the atmosphere is 100% the same year to year. Okay? So we have to shorten up the number of sig figs we use on numbers like that. Now the other ways that problems exactly like this could be written. Instead of disintegrations per second, this could have been written as what's the molarity of carbon in the material, or how many grams of carbon are in the material, or number of atoms. They would all work the same. N and N0 can be disintegrations per second. It can be grams, it can be atoms, it can be molarity. But they have to match each other. You can't have molarity up here and grams down here. Usually the problems are given to you in consistent units. And you just plug in N over N0. Okay? We'll work one more example.